Big data is undefined concept. It is very much in fashion now, and we are seeing incapacities of our technical options to efficiently analyze information that we are getting in the biomedical field, but also in many other fields, but specifically talking about biomedical field. So when we talk about finding useful information, we need to get a little bit more idea about what in this particular case I mean. When you talk about individual concept for itself has no meaning unless it is related to something else, to some other concepts. So essentially, what makes human mind understand concepts is their context and their way of how they are characterized in relations to other concepts. So let us assume we have two concepts, A and B. They are somehow related to each other. That relation is valid under certain conditions, maybe directional or non-directional, but in any way, when such a relationship is established, then we have the basic element based on which we can build what is later known as knowledge. So we are talking essentially about links between the concepts. And when we talk about big data have generally quite huge volume of linked concepts contained there, and we need systems that are going to allow us to efficiently explore such connections between the concepts, or in a specific way to extract information, extract knowledge, useful knowledge. And that also has to be somehow suitable for easy interpretation by humans. So where is big data coming in the biomedicine? Big data in biomedicine existed much before next generation sequencing appeared on the scene. It is contained in the variety of repositories of different specialized and more generic databases. It also does exist in the published documents, published scientific reports. And here is just a list of some of the resources that contain information that can be useful for the biomedical research. By no means this is an exhaustive list. There is actually more than 1,500 different biomedical databases that are operational currently, and about 450 of these are considered extremely useful, containing useful information that can be used. But what really makes things complex is not the number of entries or number of different records that exist there, but the relationships that exist between the concepts contained in these records and documents. And this is what makes data extremely big and extremely complex, and goes far beyond the capacities of computational machines that we have today to analyze that in a good way. So here is just an illustration. We have, this is a rough representation of transcription regulation network shown here as links between groups of concepts. Each node is contains thousands of entries that could be of interest there. And when you look at their mutual connections, the total number of associations that come out from such a network is huge. This is what makes really digging for useful information extremely challenging task. So in order to make finding information that is of interest for us in a more precise way and more efficiently, we need to develop systems that are aimed to what we call knowledge exploration. And these systems combine techniques from different fields, and like those that relate to information retrieval, natural language processing, machine learning, information integration, ontologies, and so on. Normally, in the biomedical domain, we always have chemistry that is playing a key role. Some molecules, be it drugs or some other non-drug components, they affect different processes in the living cells. And as such, they affect phenotypes. And so in order to find out what is going on and how it can be explained, we need a way to combine that information. This is what we try to do. So effectively, we try to provide an integrated framework where we can allow a number of these different components to take play. For example, information retrieval, entity recognition, things, information extraction, then information integration, because usually information is not in a single source where that we analyze it. There are a multitude of sources that are used, and we try to combine things. Then information enrichment, which is very important technical characteristics that enable us to efficiently sift through the big data. If we would be looking every possible combination of, let's say, associations that may happen, we would never be able to analyze that. But if we make certain sacrifices and try to consider only portions that are sufficiently enriched, then we reduce the search space and make things much more feasible. And then, based on that, we can develop different hypotheses. And finally, combining all of this brings us to more close to knowledge discovery. Of course, we are talking about automated systems which are interactive, so human interpretation of the information that is obtained is critical to actually acquire the new knowledge. So what are we actually doing? Normally, because information is not really completely anonymous, we actually know at least roughly what we are looking for. We are trying to make associations between concepts of different categories, for example, between, let's say, proteins, between organisms, between chemicals, between pathways, and so on. And these concepts we essentially capture into what is called ontologies or dictionaries, and we use these to map them to whatever different sources of information we have, and then we use that as the common indexes to extract combined information. So just as an illustration, if you look at the PubMed, which is the major reference source for published documentation in this field, it is the number of documents that are entered into PubMed database is increasing dramatically. At the moment, we have about 27 million such records, but it's approximately rising about close to 1 million documents per year. So not a single group can follow everything that is in a particular niche domain area published. So how then we come to that information? We have to have a system that is going to bring us much more description about what is contained in the what information is actually available about specific concepts we looked for. So we call this something like topic-specific database or topic-specific knowledge base, and we obtain that by providing a query to the system, which is very similar to the query for PubMed, and as an answer to that query, we get a complete database with built-in search engine that allows us to explore the associated information. And the information is combined from a variety of different resources. Just some are listed here, and so on. So, and what is currently interesting is that we can achieve this in about a few minutes for each particular query. For example, you may say epithelial ovarian cancer, human, and then you will get the tailored database as a response to this question, where you will be able to sift through the documentation and through the concepts identified in a way that is quite suitable. So you can retrieve information, you can, it is annotated in the background. I'm not going to go into any technical details there, but it enables very fast retrieval of information. You can explore information. This is the most interesting part. Actually, you can see different concepts linked together and also ranked based on their enrichment in the particular set of records and documents that relate to the query that is raised up. Probably one of the most interesting things is that for each concept that is found, you can find their so-called co-occurrent concepts from different dictionaries. Unfortunately, it's small. Here you cannot read, but each of the blocks represent concepts from particular dictionary type, and it shows a certain level of enrichment that is characterizing the link between the mother concepts and the others that are found there. Then, of course, these enrichments are quite important because they reduce the dimensionality of the search space we go for. And another way of looking at the information is we can look through that through the different graphical representations that allow us to maybe in a more simple way infer connections between different types of concepts. Then finally, we can generate hypotheses by using such systems. The most common paradigm is known so-called ABC Svensson model, where you have essentially three groups of concepts. You have concept A, you have concept C, which are not connected in any way in any of the resources that you know, but they may be potentially linked between concepts that are linking them, like you have links between A and B, links between B and C, and if you have sufficient number of such links, you may infer that, let's say, A and C are somehow connected. And the famous example is about, that Svensson used, is about deficiency of magnesium is actually associated with migraine. And there have been a number of such ABC connections based on which that has been derived. So I will talk now specifically how we can use it for drug repositioning purposes. Again, as an example, in order to deal with drug repositioning, that means finding different uses of existing drugs for the medical conditions that are not originally aimed for that drug to be used. So you need to have drug, you need to have target with which drug is going to interact, and then you have to have a disease so that the effects caused by interaction of the drug to the target will prove beneficial for the disease. So to do this, we were analyzing first how different drugs interact with different targets, and in the systems that we have, we are able to predict drug-protein interactions, but we are not able to predict specific type of interaction effect. And to do this, we are looking at the similarities between the chemicals, similarities between the targets, and also the known links between drugs and targets. And then based on that, we are able to make some machine learning models to make predictions. Also, there is another set of prediction models that we use, which are associated with analyzing different PubChem assays, different types of bioactivity assays, where based on the information that is provided, and usually it is, let's say, for example, inhibitory effect of drugs to expression of particular, let's say, protein, and usually thousands of compounds have been tested. Some did show activity, meaning that they appear to be inhibitors, some do not show, and so based on that, we develop models that can do in silico screening. So we were able, based on that, to infer potential effect that interaction of drug with a particular target may have. So using these two approaches, we did find that a drug called Ceftazidime, which is an antibiotic, and it's used for treating different bacterial infections, that it can be an inhibitor of HSD10. This is 17-beta hydroxysteroid dehydrogenase type 10. Now, among many things. Actually, when we do analysis, we are doing actually in silico screening for numerous things. But I selected this particular one because it has links to something that is, I believe, of interest. So why would this be important? Well, HSD10 has increased expression in brain of patients with Alzheimer's disease, also in multiple sclerosis. So, roughly speaking, if we predict that ceftazidime is inhibitor of HSD10, then it can actually mediate, it can actually normalize the expression level in principle for people who have such disease. And many of the drugs are actually operating on the concept that they would balance the imbalanced molecular activities in the disease state. So, well, this is, when we do computation, these are all hypotheses, these are all computational predictions. There is no real proof that these things are actually correct or not. And only the experiments, lab experiments, can really prove that something is correct or not. But then we looked, okay, so let's see, can we find somehow at least something more that would suggest that this drug actually may act as may be as an inhibitor of this particular protein. Now, we found that HSD10, when it is increased, it can lead to neurodegenerative disorders called, the most well-known was HSD10 deficiency. Now, a side effect of ceftazidime that is observed in very small number of patients, actually in 0.23% of patients, is that there are some neurodegenerative disorders and disorders of neuronal systems that can occur. So let's say, roughly speaking, it's not going against our prediction, but it cannot be really considered as some kind of proof that our prediction was correct. In any way, we searched a literature that relates to ceftazidime, and it's about 7,700 documents. And what we found is that the information that is dig from that set of documents is actually suggesting that there is a link of this drug to neurodegenerative disorders. There is link of this drug to Alzheimer's disease. There is link of this drug to multiple sclerosis. But these are, again, this is information that should serve physicians and specialists to look at that more carefully and then decide whether or not it is valid. So overall, we find that ceftazidime inhibits expression of HSD10. It's our computational prediction and requires some additional support confirmation of that. We also find that side effect of ceftazidime is that it may cause these neurodegenerative disorders. This is very weak support. In fact, I would say maybe it's not even support, it is just not going against the basic prediction that we have made. But because expression level of HSD10 is actually linked to different types of neurodegenerative diseases, then every agent that can control that in a particular way could serve as a kind of, in some form of therapeutic role. So our hypothesis is that the increased level of HSD10 in Alzheimer's disease and multiple sclerosis may be managed by ceftazidime. Thank you.